Hi statisticians, welcome to section 7.4. So last time we talked in section 7.3, we went over how to find the area underneath a normal curve, the left area. And that was using the z-score, and keep that table handy that's at the end of section 7.3. But for right now, we're going to deviate just a little bit from that topic and talk about something called sampling distributions. So let's start with a quick warm-up. This is just like a very basic warm-up about some vocabulary. So first things first, a statistic corresponds to a sample, whereas a parameter corresponds to a population. So we say a sample statistic or a population parameter. Now, some of the sample statistics that we've been talking about so far would be the mean, the sample mean, and the sample standard deviation. So like these are some of our favorite sample statistics. And remember, if we're talking about those same values but applied to a population, we use different letters for these. Instead of saying the mean, we would say mu, and instead of saying S for the standard deviation, we call it sigma. Okay, and I think I've probably just given away a lot of the answer for number 3. So with that, we're just going to do a quick matching exercise right now. So the sample mean, as I said, goes here with x bar. And again, remember, we just read this x bar for the sample mean. The population mean is mu. I'll just write that one on here just for kicks. Now, probably of the next 4, I would say that the sample standard deviation and population standard deviation are probably a little bit more immediate. So sample standard deviation, we just talked about it, that one's S. And the population standard deviation is sigma. And then so the population variance and the sample variance, remember, those are actually very related to the standard deviation. They're just the square of those values. So the sample variance goes with S squared, and the population variance, because again we use Greek letters for these, is sigma squared. Okay, so those are all the important statistics and parameters that we know so far. So again, just a note here, we use Greek letters when we're talking about a population. So we use Greek letters for population parameters. All right, and we're going to actually add one more to the list. This is called a sample proportion. And we're going to write p hat for this. So we read it p hat. It looks like just the letter P with this little caret thing on the top. And the population proportion is just given by P. So with those, let's talk a little bit more about kind of what we're doing just in general in statistics. So we talked about this a lot in chapter 1 right at the beginning of the course, but we'll just kind of revisit this idea now. Often, because to get any kind of data for an entire population, first of all, it takes a lot of time, money, maybe we're just not able to do that. Instead of doing that, we use sample statistics to kind of generally make inferences, draw conclusions about the entire population. So maybe you send a survey to a smaller group of people instead of everyone on campus. And then you use whatever data comes back from that survey. As long as you have a representative sample, you can use the data that comes back from that survey or whatever you're doing to draw conclusions about your entire population. So we do this in a few different ways. Sometimes we just estimate the value of a population parameter. So maybe we would estimate something like the population standard deviation of some value. Another thing that we do, and we haven't done this yet, we'll kind of get to this in chapter 9, is something called testing, and we'll do some hypothesis testing later. And another thing we do, which we've seen a little bit in this course, but not a whole lot, is to use what's called a regression. So we've seen things like best fit lines, that's called linear regression, to forecast what might be coming up somewhere like where we don't have exact data values. So maybe like to see what's happening just a little bit farther on down our graph, for example. So to make these different inferences, to draw these conclusions, we need to know something about the distribution of the statistics that we're using. So like we need to kind of know what the picture looks like, how these things are all laid out. So to do that, and what we're going to be doing today, is something called a sampling distribution, which is a probability distribution. Remember, this just means like a table of probabilities of a sample statistic based on a whole bunch of random samples from the same size in a population. So we're going to see a big example of this. Notice on the next page of your notes, you have this like massive table. So this all goes with this example. And fortunately for us, we don't actually have to use all the numbers on here. A lot of the statistics are already done. A lot of the work is already done for us. So this example says, Pinedale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. Only children under 12 years old may fish, and a limit of 5 fish may be kept per day. Okay, so it's this pond where kids can fish. If they catch a fish that's too small, so under 6 inches, they have to throw it back. And also, the maximum age is 12, right? So only kids under 12 can fish there. Stewart is a college student who was hired by the community last summer to make sure that the rules were obeyed and to see that the children were safe from accidents. So he's overseeing this whole thing. Each child has no difficulty catching his or her limit of 5 fish. So what that is saying is assume all kids catch all 5. Everyone brings home 5 fish. As a project for his biometrics class, Stewart kept a record of the sizes to the nearest inch of all fish caught last summer. Hundreds of children visited the pond, so Stewart has a lot of data, which is where all this stuff comes from. He selected 100 kids at random and listed the sizes of each of their 5 fish as well as the mean. So he's finding the average length of these 5 fish as well. Now, the question for us is, what is the average or the mean length of a fish caught at Pinedale Children's Pond last summer? Okay, so looking at all this data, we could, well, let me start by just talking about how this is laid out actually. So sample number 1 is what this is saying. This is basically like kid number 1. And remember, our data comes from 100 kids. So this table is like sort of in 4 different panels, but this goes all the way down to child number 100. Now, each of these kids catches 5 fish, and these are the lengths of their 5 fish. So child number 1 caught a fish that's 11 inches, another one that's 10 inches long, another one that's 10 inches long, 12 inches long, and 11 inches long. Now, of those 5, we've already been given the sample mean. So if you add all 5 of these up and then divide by 5, it equals 10.8, apparently. And this is done for 100 different kids, where we say now child number 2 caught 11, 11, 9, 9, 9, and the average of those is 9.8. Okay, so we don't have to do that hard work. Instead, what we're going to do is look at the means. Like instead of looking at all the different individual fish, we're going to focus our attention here on the means. Now, this is from 1 through 25. 26 through 50 are right here. Then going back up to the other side, 51 through 75. I hope the background noise is not too loud. And then 76 through 100. So we've got 100 different means. And now these are sample means. So again, this says X bar. It means more than 100 kids caught fish there, but we're just taking a sample of 100. So with that data, these 100 different data values, we're basically going to consider this to be our set of data. And there's still a lot. I mean, there's still 100 values to deal with. With those data values, we're going to go way back to what we did in chapter 1, and we're going to make a frequency table of those values, the X bar, the mean values. And then with that, we're going to graph this probability distribution. And we're going to see what shape it has. And remember, kind of foreshadowing here, our favorite shape and everything that we're studying in chapter 7 is normal. So hopefully that is what we see. Okay, now let me give you a couple of reminders here. This is on your table of formulas, and you actually don't have to use it right now, but the class width formula is the upper value or the upper limit minus the lower limit, all divided by the number of classes. And then remember, you increase this to the next highest integer. You do this even if you end up with a whole number here. You still bump it up to the next integer. Now in this case, this problem actually tells us use a class width of 0.38. And there's basically, like, the reason for that is just to make our values a little bit friendlier. So you're going to have to trust me on that one. And also you're going to have to trust me on the lower class limit here, because I'm going to do something weird. If you look back at this table and find the lower class limit, and I won't make you hunt for it too much because there's 100 numbers here, but if you look through all of these and you find the lowest value, it's right here, it's 8.4. So this is the minimum value in all of these 100. And also, if you search through all of these to find the highest value, and I won't make you do it unless you want to. If you want to, pause the video right now. But I will do it for you. It is right here. It's 11.8. That's the maximum value. So if we were finding the class width on our own, I would take 11.8, I would subtract 8.4, and then I would divide by the number of classes, which based on this table looks like we're doing 9. I'm telling you, just take my word for it, we're going to use a class width of 0.38. The other thing that we're going to do, even though the minimum value was 8.4, we're going to do something a little bit weird, and trust me, this is for your own good, just to make the values a little bit friendlier. I'm going to use, 8.39 here. Okay, so that's where we're starting on this table. Now, the class width of 0.38 comes in here. Remember, the 0.38 is not the distance to get to the upper class limit, so don't fall into that trap. It's actually the distance between the two lower class limits. So I'm going to go plus 0.38, and then here plus 0.38, and so on. And so pause the video now and fill out that first column. So when you have this done, it should look like 8.77 and then 9.15. Check your values with my values, 9.53, 9.91, 10.29, 10.67, 11.05, and 11.43. Okay, so that's just adding 0.38. There's our class width that I'm adding to each of these. So now I need to find the upper class width. And basically, this one's a little bit easier to do. Essentially what I want to do is like get right up against this 8.77 without actually touching it. So I'm going to say 8.76. And now because all the values are actually, let's see, expressed, well, they're expressed to the nearest tenth. Let's see, these values are expressed to the nearest tenth, so that's fine the way that it is right now. I'm going to be cautious about this actually. No, this is fine. Okay, so 8.76 and then 8.77. There won't be any overlap there, and we'll have all classes accounted for. Okay, so then up against 9.15, I'm going to do 9.14. And then 9.52 is just a smidge under 9.53. So fill out this column. .66 and 11.42, and then the largest one here is 11.80. Now, if you're concerned about how we got this one, because you don't have that next lower class limit to kind of just base your answer from, you can check, like example, you can do in your calculator 11.42 minus 11.04. And what you're going to find is there's a 0.38 difference. Actually, there's that class width again. So you're going to find that this is 0.38. And so another way to do this is just to take this value, 11.42, and again add that 0.38 class width, and you'll find that next upper class limit. So now that we have those, okay, that's the easy part of this whole thing. Now the rough part starts. So what you're going to have to do, and I apologize for this, is go back through that massive list of 100 values and find the frequency, find the number of values in that list that's, for example, between 8.39 and 8.76. So we're trying to figure out how many values are in each class. Okay, when I look back at this, there are, so the first class was 8.39 to 8.76. Now there weren't that many values in the 8 range, and I think actually it's just this one. So on my next page, I'm going to say there is just one value that's between 8.39 and 8.76. Now 8.77 to 9.14, so class number 2. Not that way. Basically 8.8 to 9.1, because everything on the other page is rounded to the nearest tenth. So going through this, 8.8 to 9.1. Well, here's one. Here's another one. 8.8 to 9.1. Here's a third one. Now look in the bottom part. Here's a fourth one, and here's a fifth one. I think that's it. Okay, so there's 5 in the second class. Now, you should pause your video now and fill out the rest of this frequency table. And since I'm sure all of you did that, I will just say check your numbers with my numbers. 10, 19, this is the class that's really terrible. Class number 5. There's 27 of those values in there. Then we start dropping down again, 18, and then 12, and then 5, and then 3. Okay, so remember, there's 100 values total, and one of the ways that you can check, especially on a problem like this, where there's a whole lot, it's like a significant amount of data, you should add these all up, and they do add up to 100. So everything has been accounted for here. The next thing we're going to do is take this and find the relative frequency. So because there are 100 data values total, this is the total number of values. I'm going to take each of these frequency values and divide them by 100 to find my relative frequency, and we'll express this in decimal form. So like if I take 1 and divide it by 100, that gives me 0.01 relative frequency. For the second class, I'll take 5 divided by 100, which is going to be 0.05. Again, you should pause your video now. This column is actually very doable. So pause your video and come back for the answers in just a second. So you've had a chance to do that. Check your numbers with my numbers. 0.18, 0.12, 0.05, and 0.03. These are all pretty easy. You just kind of move the decimal point back twice. It won't always be like that on any of these tables, but in this particular one, because we do have 100 total data values, it makes our computation in that last column fairly friendly. So this is our relative frequency table. And if you add up all these relative frequencies, notice that they all add up to 1. The sum of this entire column equals 1. Now, that is not related to the fact that there's 100 data values. Your relative frequency should always add up to 1. So because of that, we can kind of think of these decimal values as probabilities. Like we could think of 0.18 as 18%, for example. So essentially what we've done in creating this table is created a table of probabilities, which is called a probability distribution. Probability distribution just kind of means like a table of probabilities in different classes. So with that probability distribution, which we've just created, we're going to make basically a histogram of the X bar values. So we'll use the classes, these guys, across the horizontal axis, and then we'll use the relative frequency values on the vertical axis. So that's where this is going to go. So here's going to be the y-axis, and these are going to be along the horizontal axis. So I'll get you started on that, and then you'll pause the video again, but let me at least let you know how to scale this thing. So here's my recommendation. I'm going to make my pen a little bit smaller here, small space. Here's my recommendation for this. Our smallest value on that table is 8.39. So I kind of want that to start right here. And the largest value was 11.8. However, remember, when we're doing these classes, when we're making any kind of a histogram, we always want these bars to meet up. So there was that idea that we talked about in the beginning where you want to fluff up these bars. So I'm going to make that first bar go up to 8.765. And then this one would sort of fluff down to 8.765. And this one would fluff up to 9.145. This one is also going to fluff down to 8.385, and so on. And this is going to make all of our bars on our bar graph sort of flush. Okay, so I'll start that here. Here is 8.385, and that first bar is going to go up to 8.765 and 9.145. All right, so pause the video and fill out the horizontal axis. So when you've done that, you should check that your numbers correspond with my numbers, 9.905 and 10.285, 10.665, 11.045, small space here, 11.425, and then I have one more bar, so I'm just going to do the best I can here, and that is 11.805, which was that 11.8, but then just moved up a little bit. Now, we always want to label our axes. So actually, before I go any further, let me label this. Remember, these values that we're talking about are the average length of fish in a fishing pond. So let me put that on this table. That's my horizontal axis. Average. Actually, let me be more precise than that. I'm going to say mean length of fish in a fishing pond. All right, and then now across the vertical axis, I needed to label those probabilities. So looking back at my relative frequencies or probabilities, that's kind of what we're doing here. These are probabilities. My smallest one is 0.01 and my largest one is 0.27, so almost 30%. So I'm going to use that here. Let's see, I think we have room to scale by 5s. So let me do it this way. 0.05 and then 10 and 15 and so on. And that'll fit nicely. Okay. And then of course we want to label our y-axis as well. It's going to be really hard for me to write vertically on this tablet, but oh my goodness. The probability, because we are making a probability distribution, so we should have something about probability. The probability of catching this average length of fish. Okay, yours will look nicer than mine. So now we're going to fill out these bars. So looks like in that first class, we've got a 1% probability or a 0.01 relative frequency. Okay, so 1% on here. Oh, you know what? I forgot to do something really important. Let me put that little break in the graph right here because this scale is not consistent. Like if this is 0 and then we jump to 8, that's not a consistent scale. So be sure to do that. All right, so 1%, well, if this is 5, this is 2.5. I'll just kind of do the best I can here. Here's 1%. The next column or the next class had a 5% probability. So there's my second bar. And then one last time here, pause the video and fill out the rest of the table and come back when you're done. Third class is 10%. Fourth class was 19%. Yours should be already done since you're back and watching this. 19%, then we had that big one, 27%, really close to there. And then we start dropping back down. So 18, and then 12, right there. Now as we're doing this, you should kind of recognize this shape, the shape of this distribution, and then 3%. You should recognize the shape of this distribution. I can't really color these in very effectively, but I'm going to. I feel like graphs don't look complete if I don't color in the bars somehow. I don't know. Okay, you should recognize the shape of this distribution because it's our favorite shape. It looks vaguely normal. It looks generally bell-shaped. Turns out this is not a coincidence. So one of the things that we're going to see in section 7.5, what we're going to see coming up next, is that if your original data if your x values have a normal distribution, then your x bar, your sample mean distribution, will also be normal. Now, there are some conditions and special cases here. We'll see all of this in detail in section 7.5, but for right now, this is just kind of a happy example. Oops, normally distributed. So this is just sort of like a pleasant surprise that we can see that this sort of follows, let me try again. This sort of follows a normal curve here. So there is a problem here on the back. Just cancel that entire thing out. There's a lot of problems with that. So don't worry about that one. You're ready to do the section 7.4 homework, and I'll see you back here at in 7.5.